circles unit. This is everything we've learned so far. So you don't need to take notes on this, but you do need to look up here and watch. Okay, so this is everything we've learned so far. So we learned on the first day about central angles. We know a central angle is an angle that starts at the very center of the circle, works its way out. And we learned a central angle is equal to its intercepted arc. So if this is 30 degrees, arc AB is, the measure of arc AB is 30 degrees, right? Now if arc AB is 60 degrees, what's our central angle?
Theta.
What is our central angle if the arc's 60 degrees?
Oh, 60.
60 degrees, good, okay. Then we learned how to find physical arc length. So remember, if we want to know the physical arc length, and we're dealing with a central angle, it's radius times theta. As long as theta is in radians, because radians is the physical distance. So we kind of first converted our theta to radians, and then we multiplied by the radius. Because remember, a radius, obviously, your arc length of a huge circle is going to be much larger than a smaller circle. Even though they could both make a 60-degree angle, the arc length's not the same. That's why we have to consider it in our radius. Then we learn how to find the area of a full circle. It's pi times radius squared. That would fill in this entire circle, right? And we know that if we want to find only the area of a sector, which just means area of a section of the circle, so for example, this piece theta, then it's that piece over 360, so theta over 360, and it's still pi r squared. Because area of any circle is pi r squared, right? And we learned, okay, the only difference in this one is we only want this out of the full circle, right, everybody? Okay. So today we're doing 8-4. We're going to be dealing with tangent lines on a circle. So, first of all, I'm teaching you what a tangent line is. Here you go. A tangent line is tangent to a circle if it intersects the circle at exactly one point. So I'll say that again. A line is considered to be tangent to a circle if it intersects a circle at exactly one point. So in this picture right here, this line right here is a tangent line. You see how it intersects the circle? It touches the circle in one spot only. That is considered a tangent line. Now where it touches down, that one spot where it touches, that's considered the point of tangency. So we just need some vocabulary here. So here's our tangent line. It only intersects the circle once. That's what makes it tangent. And where it intersects at that one spot is the point of tangency. Questions on that? So let's look at some examples of some non-tangent and some tangent lines to a circle. So right here, this first is a tangent line. This line is tangent to the circle because it intersects in one spot, and boom, right there where it intersects is the point of tangency, right? Yeah? Okay, now look. Is this line tangent? No, look, it intersects a circle in two spots. Now, do you guys know, just a reminder, from here to here is considered a chord on a circle. Just a reminder. Okay. Now, looking right here, is this line tangent to the circle? No, it's touching in two spots. Now, this is where people say, oh, okay, well, this must be tangent to the circle because it's only touching the circle in one spot. But you've got to consider, you can extend a line, right? If you extend that line, isn't it going to touch again? So this would not be considered a tangent line, because if this line was extended, even if there's not an arrow, it would touch twice. Does everybody understand? Not tangent to a circle, yes?
Also, just saying, because it's inside the circle, it happens inside the area of the circle, which is also part of the circle.
True, yes. Absolutely, you can think of it that way as well. Okay, questions on that? Okay? So now, here we go. This is the big thing that we're learning today. So now you know what a tangent line is. So here's the big thing. If you drop a radius to the point of tangency on a tangent line, then that creates a 90-degree angle to the tangent line. So I'm going to say that again. This is the big rule that we're learning today. So it says, if you drop a radius, so do you see how from here to here I'm dropping a radius? Yeah? To the point of tangency. Does everybody see the point of tangency? If you drop a radius to the point of tangency on the tangent line, it's going to create a 90-degree angle at the point of tangency. Okay? So if this is 90 degrees on this side, will this also be 90 degrees? Okay. So that's the big thing. If you drop a radius to the point of tangency on a tangent line, it will create a 90-degree angle. And then we're going to be seeing things like this. Now, won't that just be a right triangle we're looking at? Yes. Okay. Questions on that? So does everybody have that rule written down? So number 23. Most of my examples, for the most part, are coming off your worksheet. So number 23, it says, determine if the line is truly tangent to the circle. So first of all, with these, we've got to determine which line are we talking? Which line is tangent? So looking at this picture, is this line right here a tangent line?
Yeah.
No, right? Isn't that a radius?
No, yeah.
Isn't it touching the circle twice if we extended it down? That's not the tangent line. Now this is where people say, well, is this the tangent line or is this the tangent line? So I'm going to ask you a question. On this line right here, if we extended it this way, would it touch the circle in two spots?
Yes.
Therefore, that's not the tangent line. Well, then isn't this the tangent line? Look, doesn't it only touch the circle in one spot? If we extended that line, wouldn't it still only touch in one spot? Yes. Okay. Yes.
So the hypotenuse can't be the tangent.
Right. It will not be the tangent. Okay. So we just learned the rule. If you drop a radius, which is from here to here, right? To the point of tangency, wouldn't that be there?
Yeah.
Then it's going to create a 90-degree angle. So now we're going to determine, is the line truly tangent? If it is tangent, that is 90 degrees. And now don't we just have a right triangle here? So if we have a right triangle, this has nothing to do with tangent lines, but if we have a right triangle and we're talking side length, won't the Pythagorean theorem always be true if you have a 90-degree angle? Yes. Okay, so let's first figure out here what we're looking at. This is one of the sides, right? And then the other side would be this. So 3 square roots of 3. And our hypotenuse is, well, let's be careful here. Okay, so our hypotenuse is, if this is 3, if I draw a radius here, won't it be 3?
Yeah.
Here's 3, so from here to here must be 3. Okay, so our hypotenuse is across from 90 degrees. Make sure you use the whole hypotenuse, won't you do 3 plus 6? So that is 9. So we're doing, our hypotenuse is 9. Is anybody confused at how I drew that right triangle? So now we'll check. If that truly is a 90-degree angle, then the Pythagorean theorem will work. So we know side 1 squared plus side 2 squared must equal the hypotenuse squared. So we have side 1 squared, which is 3 squared, plus side 2 squared. Now this is where, when we first were doing this a long time ago, but not now, we were making lots of errors. Isn't it 3 square roots of 3 all squared?
Yeah.
So we've got to put that in parentheses. 3 square roots of 3 all squared is equal to the hypotenuse, which in this picture is 9 squared. Now notice we're not solving for anything, we're checking if this works, because if it's 90 degrees, the Pythagorean theorem has to work. So let's type it into our calculator. I want every single one of you typing, because this is where most people get it wrong. So we have 3 squared, which is 9, right? Now this next part, you have to type it into your calculator correctly. So everybody should be doing this. Hit parenthesis first, then hit 3. So parenthesis, 3, then do the square root of 3. You've got to close your parenthesis around the square root of 3, then you've got to close it around the full thing. So there'll be a double parenthesis on the end. Does everybody hear me? Then hit squared. You should get 27. If you didn't, you typed it in wrong. Now here, let's think about the math behind why it's 27, guys, because we should be able to think about the math. So let me come up here for a second. 3 square roots of 3 all squared. There's no plus sign, right? So don't we just square both things? Yeah? So that's 3 squared and the square root of 3 squared, right? Squaring each of those things. What's 3 squared? What's the square root of 3 squared?
3.
Doesn't the root cancel out the power? So 9 times 3 is 27. Okay. And that's equal to 81. Is this a true statement?
No.
27 plus 9 is what?
36.
So we have 36 is equal to 81. No, that's not true. Therefore, this was not a right angle, okay? Because if it was, the Pythagorean theorem would have held true. So we would say, no, this line is not tangent, because if it was, that would have been a 90 degrees. So that must have not been 90 degrees. So that line was not tangent. Does that make sense?
How is that possible? Like,
Because the picture could be deceiving. It could be,
if we would have zoomed in, there would have been like 2 places that would have touched that.
or when extended, it will cross again.
Oh,
Yeah. If it's not tangent, then it's going to cross twice.
right.
Okay? Okay, here we go. Determine if the line is truly tangent. So I'm doing the second one on 23. So once again, right here is my tangent line, right? This one's definitely not. It would cross twice, and then this one's a radius, right? Now we know if we drop a radius to the point of tangency, which is right there, it will create a 90-degree angle. If it's truly tangent, now we're determining if it is a tangent line. So we once again have a right triangle. Our hypotenuse is, let's be really careful. This piece is 12, but if this radius is 4.5, isn't this radius 4.5? So the hypotenuse is actually 16.5. So we've got to make sure we do this correctly. So this is 16.5. One of the sides was 4.5, and then the other side was 10. So we'll be doing side 1 squared, 4.5 squared, plus side 2 squared, 10 squared, equal to the hypotenuse, which has to be 16.5 squared. Go, type it in. 4.5 squared plus 10 squared. You get 120.25 is equal to, type in 16.5 squared. You get 272.25. So was that right triangle truly a right triangle? No, the Pythagorean theorem didn't work. And if it was a right triangle, it would have. Therefore, that must not be a 90-degree angle. Therefore, it's not tangent. Okay. So last one on 23, then I'll let you go. So last one on 23. So it said, determine if the line is truly tangent to the circle. So once again, here's our tangent line. It's touching down at the point of tangency right there. And we have a radius drop to the point of tangency. Therefore, this is our 90-degree angle. So now it says this radius is 5.6 and this says 10.6 written right here. So that must be the full length, right? Okay. So we're doing side 1 squared, which is 9 squared, plus side 2 squared, which is 5.6 squared, is equal to 10.6 squared. Let's see if this comes up with a true statement. So type it in. 9 squared plus 5.6 squared is 112.36. That's equal to 10.6 squared. You get 112.36. So was that a 90-degree triangle? Yeah, isn't that true? Yes, therefore this line was truly tangent. Questions on how to do that? So right now we're just determining, do we have a tangent line? Okay, so last one, okay? Here we go, quick. This one's really quick, so just look, don't take notes on this one. So first of all, we've got to figure out which is the tangent line. It's definitely not that, isn't it? Intersecting the circle in 2 spots. Definitely not that, intersecting the circle at 2 spots. This must be the tangent line, so there's the point of tangency. If you drop a radius to the point of tangency, it creates a 90-degree angle. Now careful, we just have a right triangle, but if this is 2, and it's right there, it's not in the middle, then what's this? 2, good. So wouldn't this full length be 4? So we'll be doing 4 squared plus 3 squared must equal the hypotenuse, which is 5 squared. So guys, that's 25 is equal to 25. So, yes, I didn't mean to cross it out. That does work, right? So yes, this line is tangent. Questions? Okay, sweet. Do 1 through 8. So now, notice in that we weren't given any unknowns. Now we're going to be given an unknown, and we're going to use what we just learned to solve for that variable. So it says, find the missing length and assume that lines which appear to be tangent are tangent. So in the instructions, it's telling us if the line looks to be tangent, it is indeed tangent. So we're told it's tangent. Okay? Does everybody understand the difference? So we're not testing if it's tangent.
For sure.
We know it's tangent for sure. So, let's look here. Which line is tangent? Is this the tangent line? Is this the tangent line? This is the tangent line, right? So here's my point of tangency. If you drop a radius to the point of tangency, it creates a 90-degree angle. So now we know that for sure is a 90-degree angle, therefore the Pythagorean theorem will work. So now we can use that to solve missing side lengths. So don't we just have a right triangle here?
Yeah.
So side 1 squared plus side 2 squared is equal to the hypotenuse squared. Isn't this my hypotenuse? Okay, so side 1 squared, x squared or 4 squared, doesn't matter the order. X squared, side 1 squared plus side 2 squared is equal to the hypotenuse, which is 5 squared. Now, keep in mind, if the original problem didn't have decimals, we probably won't use decimals, okay? If your original problem had decimals in it, yes, you'll use decimals. So let's go through and solve this one algebraically. We have x squared plus 16 is equal to 25. Solving for x, isn't this quadratic?
Minus 16.
So we would subtract 16 from both sides of the equation. So we have x squared is equal to 9. So then what would we do?
Square root.
Square root both sides of the equation. So we get x is equal to, what else?
Square.
No, 3 squared is 9.
X equals to 3.
So think about this, guys. Think about this. What squared is equal to 9? 3 squared. What else squared is equal to 9?
1.
What's 1 squared? 1, right?
9.
Think about it before you answer.
I don't know.
1 squared is equal to 9, besides 3.
Nothing.
What were you saying? 3 squared?
3 squared is equal to 9.
There's something else that's equal to 9.
1. 9.
9 squared is not equal to 9.
You just said 1 squared is equal to 1.
Because 1 times 1 is 1.
Oh my hell. I don't know what you're saying.
Oh dear.
4.5 times 4.5.
Wrong. Try it. There you go, Martin. Way to remember that. When we're solving a quadratic and we take a square root, what do we have to account for? Plus and minus. Now, why is that? Because positive 3 squared is 9. Isn't negative 3 squared 9? Yes. Okay. So x is equal to plus and minus 3. Does everybody understand now why? Okay. You don't understand that 3 squared is 9.
Yeah.
Do you understand that negative 3 squared means negative 3 times negative 3? What's that? 9. So you don't understand why when we take the square root, we have to account for the plus and minus.
Right.
So now, in the context of this particular problem,
We're only using
would we put in a negative 3? Would a radius ever be negative? No, right? So we throw that answer out. But you have to remember, when solving quadratic, that answer is there, correct? Everybody, do you understand? Okay. So we throw out negative 3, so x is equal to 3. That's the answer we keep. But if I was said solve and you forgot the plus and minus, which 90% of you do, you get it wrong. Yes.
Can we just take the hypotenuse squared and subtract it from the 4 squared?
That's exactly, you're doing the math in your head, and that's exactly what you're doing, right? That's the algebra behind it. Because when you take 5 squared minus 4 squared, right? Yeah. Okay. Okay, let's do another one. So looking at the picture here, we've got to be careful. So it says, assume the lines which appear to be tangent are tangent. So first of all, this is not the tangent line, neither is this. This is the tangent line. Here's the point of tangency. When we drop a radius to the point of tangency, it creates a 90-degree angle, correct?
Yeah.
Now very careful here. So we have, I'm going to draw this one out. We have a right angle. This side is what?
3.
If this radius is 3, what's this radius?
3.
So therefore the total length would be, so this is 6, our hypotenuse is,
6.
oh crap, I forgot that this one's not going to work.
Yep, I knew it.
If you have 6 and 6, you can't have a right.
Right, I meant, when I put this example, I meant to have a 2. So that was my fault.
Oh.
Sorry about that. So this is 2, so this is 2, so this is 4. So this is 4, our hypotenuse is 6, and then this is, so now we know side 1 squared, 4 squared plus side 2 squared is equal to the hypotenuse squared. So we have x squared is equal to 6 squared minus 4 squared, right? Okay, so what is 6 squared minus 4 squared?
20, 18. 12.
20.
20.
That's what I said.
Okay, so then when we take a square root,
Yes.
okay, so we have x is equal to the square root of 20. Now, is that a decimal? Did the original problem have decimals? No, so let's break it down by hand. So we have 10 times 2, right? 5 times 2. Now we can pull out roots of 2s. Now it's not 2s. If there's 2 smiley faces, they can leave, right? So we pull out a 2, which is technically the square root of 4, correct?
Right.
Which, so what are we just pull out a 2, right?
Right.
So we have 2 square roots of
5.
5. So that would be our answer. X is equal to, and it's plus and minus 2 square roots of 5, right? We throw out the minus for this problem. So 2 square roots of 5, which is approximately, decimal, let's just write down both. So 2 square roots of 5, 4.5. So I would write 2 square roots of 5. Does everybody understand? Yes.
So when you have to use both the plus and
You never do.
When you're solving any quadratic and you're missing the x, which we were here, right? Square root both sides, you have to account for the plus and minus. Now in the context of this problem, since we have a side length, it's not going to ever be negative. We throw out the negative answer. So yes, these are, we're all going to throw them out, but we've got to be thinking about the fact that we have both answers. Yes?
how did you get x squared equal to 20? Yeah, 4 squared.
Because you'd subtract, this is 16, right? This is 36. So take 36 minus 16 to get x alone. That's 20. Does that make sense? Good questions. Okay, so you're going to do, oh, one more, okay? And then I'll let you work. So looking at this picture, it says, assume the lines are tangent that appear to be tangent for solving for x. Are we dealing with Pythagorean theorem?
60.
No, right? Pythagorean theorem is side lengths. Do we have side lengths here? No, we have angles. Okay? So now we know that this is the tangent line. If we drop a radius to the point of tangency, that creates a 90-degree angle. Now, don't we have a triangle? What do we know about the angles of a triangle?
Equal 180.
They add up to be 180. So to find x, when we take 180 minus 30 minus 90,
60.
60 degrees. So this must be 60 degrees. Does everybody understand? Angles of a triangle were different. Okay. So you're doing 9 through 12. Now all of those start with decimals. So you can use decimals on 9 through 12. Because your original problem had decimals, therefore it's acceptable to have a decimal answer. And then you're doing 19, 20, and 21. Now understand something. If I have a picture, so I'm going to give you a hint on one. If I have a tangent line, just because there's not a radius drawn, can't you draw your own radius in?
Yeah.
So wouldn't that be 90 degrees to the point of tangency? So think about that, okay? So continue. Number 22, I'm going to do with you, one of them, okay? So first of all, we're asked to solve for x. Lines that appear to be tangent are tangent. So this is our tangent line. Right here's our point of tangency. If you drop a radius to the point of tangency, it creates a 90-degree angle. So now from here, we know side 1, we know side 2, and we know our hypotenuse. Because even though if this radius is x, then this radius is x. This piece is 6. So wouldn't our hypotenuse be x plus 6? Now I had some people say, so that's 6x. That's x times 6, right?
Right.
This is x plus 6. Can you
Yeah.
combine x plus 6? No. So our hypotenuse is x plus 6. So just because it's different, we know that the Pythagorean theorem will work. So side 1 squared, which is x squared, plus side 2 squared, which is 9 squared, is equal to the hypotenuse, which is x plus 6 all squared. Right? The hypotenuse all squared. Everybody comfortable with that? Okay, so right now we have x squared plus 81, because 9 squared is 81. Now, some honors classes in this school would say that this is just x squared plus 36. Is that x squared plus 36? Absolutely not, right? We know better than to break the forbidden rule. Can we do that? No. So wouldn't we rewrite it as x plus 6 times x plus 6? We don't have to just square that because of the plus sign. So we're going to have x squared plus 6x plus 6x, and then 6 times 6, don't add those. I have people add those all the time. It's 36. So over here on the left, we still have x squared plus 81. On the right, I'm going to combine like terms. I have x squared plus 12x, because 6x plus 6x is 12x plus 36. So now we would say, before we go about solving this, shouldn't we combine all of our like terms?
Right.
Okay, so let's do that. Let's bring our x squareds together. You don't float them together. You do algebra to get from one side of the equation to the other. So I'm going to subtract x squared from both sides of the equation. So I have 81 is equal to, what's x squared minus x squared? Didn't that have to be 0? That happened to add up to be 0, right? So we're left with 12x plus 36. And phew, our x squareds cancel out luckily in this problem, because now we're not solving a quadratic, luckily, right? But we could solve a quadratic, right?
Right.
Okay, this one's not quadratic anymore. We're just solving. So don't we just isolate x?
Minus 36.
So we subtract 36 from both sides of the equation. So we're going with 80,
5.
81, yep. Okay, so we have 45 is equal to 12x. Then we divide both sides by 12. So x is equal to, what is it?
3.7.
3.75. Yeah, we could write that or the fraction. I'm okay with that answer for now. So that's good enough for me. So that's 3.75. Questions on how to do that? Okay, I'm going to give you a couple minutes to do the rest of 22. Very similar, guys. 1. Look up here, guys, because this one's a little bit harder. And if you're going like my first hour was, you're probably getting them wrong. So here's the next example. I started out with an easy one on purpose. So we've got to go through and find the perimeter. So we've got to go through and determine what we know. Because if this is 10, that's not from here to here. So you can't say, oh, that's 10. Does that make sense, everybody? So we've got to work our way around and use what we know. So we do know from here to here is 2. It shares an angle. So what's from here to here?
2.
2. So now think about it. If the full length is 10, what would this piece be?
8.
This is 8. So if this is 8 from here to here, what's this from here to here?
8.
Good. Now looking at this piece carefully here. We have this piece is 1 from here to here. So from here to here would be 1. 1. Good. So then if the full length is 7, and this piece is 1, we can do 7 minus 1 to figure out the leftover. If this is 6, then this is 6. So now we can add the perimeter very carefully. So carefully, I'm going to cross them out as I go. A lot of people will mess up because they'll either double dip or leave something off. So I'm doing 7. Is everybody following me? So I cross them out so I don't miss anything. So I'm doing 7 plus 6 plus 2. I'm not going to double dip and do plus 2 plus 10, right? So this whole length is 10, so I'm going to do plus 10. So that was this. Then plus 8, or this, plus 1. We wouldn't add up this one because we did a full length of 7. Does that make sense, everybody? So you get 34. So don't double dip when adding up the perimeter. Any questions on that? Or don't leave anything off. We're all good?
Yes.
Okay, so now you can finish the worksheet.
That's just.
Just looking up here real quick. See how this tangent line and this tangent line share an angle?
Right.
That's where they're equal. A few of us are saying that this is equal to this. They don't share. That's just a tangent line in general. Those are not equal. They're not going to necessarily be cut equal. So once again, this tangent line will be equal to this tangent line, but not necessarily this will be equal to this. Not true. Okay? So just be really careful.